Let me also start out by thanking the organizers for organizing this really stimulating meeting and for including me. It actually brings a lot of, coming here brings back a lot of memories. I walk around the hall, I saw these pictures of the people who are here. 20 years ago, I was fortunate. Walter asked me to join him to do this project for the school children in California in memory of the centennial of the photoelectric effect of Einstein. And we did this film called The Power of the Sun. And it's interesting that back then we never saw that solar energy would be able to compete with fossil fuel. Today, California, electricity from solar is cheaper than fossil fuel. It's an amazing thing the society has done in really move mountains. I think about 3 orders of magnitude cost reduction in that. On the other hand, we still talk about same topic of high conductivity. It's telling you how challenging and difficult. But I do want to echo one thing Sophia said earlier. Despite all this, the field has progressed a lot. Really, we understand a lot, but it is a very hard problem. Okay, so that's what I'm hoping to convey today is these 2 topics. One is all from the electron-doped cuprates. One is the Bogoliubov quasiparticle on this Gaussian Fermi surface, and the other is the unexpected low energy gap. Namely, there's more superconductivity in this long-range ordered state. That's what we think. And if there's time for discussion, then to make the connection with the theme of this topic, then I'll talk about the whole doped system. Okay. So we focus much of our attention on the whole doped cuprates. And the electron doped cuprate seemingly much simpler, long-range order than small bubble of superconductivity. Okay, so that's what I'm hoping to do. The first topic is somewhere near optimum doping. Okay, and the second topic is in this regime where there's a long-range order. So these are the 2 topics. And as again, if there's time, I'll try to make a connection to the theme of this.
What is the green shading supposed to represent?
Charge density wave. That's from the literature, yeah. Okay. I hope to draw 2 more lines inside the end of the talk. Here are the collaborators and the photomeasuring experiments done by the team at Stanford, also at the KTH. We use also their facilities. And really, I would like to highlight the work of Ben Chu. He really is the student who's driving this effort, and also then we benefit tremendously from the theory collaborations done by Li, his collaborators Zhang Li, and also Tom Devereaux. So this is really a long-term collaboration, and the samples grown earlier by Yang Li's group, and more recently they were grown by 2 of the graduate students in my group. And we also have specific heat measurement from NGS Reed. Okay. Briefly, angle resolved photomation, you have photon in and you jet electrons. And you take an image. What makes photomation so efficient is the fact that hemispheres are fantastic imaging machine. Therefore, how the electron enters this hemisphere can be directly mapped onto the detector. So once you know where the electron is on the detector, you know the angle of electron coming in. From that, and the fact that you can measure the energy, you put a positive voltage here and negative voltage here. Only the electrons with the right amount of energy will be able to go through. So you know the energy and the direction in this multi-channel way. That makes this technique powerful. A lot of data comes. So that's really kinematics. You can get energy momentum information. Okay, of course, for this audience, we are measuring other than the matrix element and all the single particle spectral function. The cuprates, okay, just a notation, everybody knows that in this case, the electron doped system really is a single band problem. And when I talk about no means 45 degrees, and when I talk about anti-no means the zone bound direction. Okay. Now, here's a cartoon view of this. If you would take a Fermi surface that we say I have a long-range anti-ferromagnetic order, then I'll fold the Fermi surface. Depending on the interaction, you gap this region, and you have a reconstructed Fermi surface. That will be what it will be. Okay. Then, depending on the doping and the details, this part of the pocket could be above or below the Fermi level. What I'm going to talk about for the first part is this part is below the Fermi level. Right at the cusp, this was below the Fermi level. Okay. So the takeaway of this will be, if you will have a reconstructed Fermi surface due to a much higher energy scale spin density wave, okay, then you will say, okay, I reconstructed Fermi surface, then I would open up a superconducting gap on top of this reconstructed Fermi surface. That's what will be the expectation. Okay. What I'm going to tell you is that no, the superconductivity actually has a maximum of the superconducting gap at the so-called hot spot, means that the original Fermi surface crossed anti-ferromagnetic zone. Okay, that's where the maximum is. In fact, it's not on the reconstructed Fermi surface. That's the takeaway I'm hoping to make a case for you. Now,
which doping was that?
That's about some 15% doping. Okay. Eventually, the other one merges. So that's in this doping region. You can see that this is well accepted. That there's a crossover from a reconstructed smaller Fermi surface to a larger Fermi surfaces in the literature. In fact, this kind of physics is already there in Peter Armitage's thesis work, and you can see the hotspot, and that's 2 decades ago, and that's widely seen in the literature. Okay, now more recently, we asked this question: can we see basically the other side of the Fermi surface? Usually, you only see one piece, and indeed, in the electron doped system, you begin to see the folded band of that. And this happens in this regime, okay? In this regime where Martin's group has shown that it's sort of 2-dimensional magnetic order, it's a commensurate, okay? That's where they go. So now, again, here's the reconstructed Fermi surface. Your expectation will be gap on top of this Fermi surface, okay? Because after all, superconductivity happens at a much lower temperature than what is perceived. Now here is really the experimental progress. The sample and the measurement was good enough. We were able to identify the Bogoliubov quasiparticle, which tie that to the superconducting state. Then you can make a statement, and you can see that it shows a maximum here, in between this Fermi surface. That's where the gaps are largest. That's, of course, also where the anti-ferromagnetism. So let me just say the experimental progresses. Again, that's the data from Peter's thesis 2 decades ago. Back then, we would not be able to see this temperature dependence, show this to be a superconducting gap. We're just using the leading edge, and that's a Matsui et al. Show similar work, and they begin to show that, hey, this thing was non-monotonic. You see, okay, that's 2005, okay? So this thing was, back then they say, okay, this is just higher harmonic of a D-wave gap. Okay, that's where it is. But the key question was that because we also have a pseudo gap in similar momentum space, is just the residual, because it's small effect, residual of this pseudo gap. Okay, so that's where things stand, and that's the more recent data looking into that. You can see cut 1, 2, 3, and 4, 5, and you see cut 1 as a round node. Well, this sample is about TC of 25 Kelvin, and you can see this guy sort of bang back. Did not quite reach the Fermi level. That means the nodal piece is more like a dashed line. On the other hand, look at cut number 6 here. The antinodal piece is very clear. Okay, reach the Fermi level. Now, it's immediately clear that in this spectra, at this point, you can see there's a huge spectral suppression. In other words, the antiferromagnetic band bangs back 100-some millivolt below the Fermi level. Okay, that's this red feature. Okay, ignore the green for this for the purpose of this talk. That's the antiferromagnetic reconstructed Fermi surface. Then you notice that, in fact, there's a residual spectral wave inside the magnetic gap, okay, in this region. And if you trace out, they actually were there sort of, in other words, otherwise the band structure, the two pieces, there's a higher energy antiferromagnetic structured band gap, and there's a residual state. The question will be, is this residual state is just a trivial disorder? It can also give that to you. That will be the test. Okay, so again, let me show you. I go from here to here, okay, in the K-space, spectra each taken from one by one. You see this feature? This band grew to the higher energy and show up the maximum somewhere here. That's the hotspot. Of course, that's the largest part, the antiferromagnetism happen. But if you look carefully, you also see another one, okay? This at much lower energy and show up also at maximum, furthest away from the Fermi level, and this one basically shows a peak in this spectrum. Now, if I would take one slide, then that is the one here. Okay, that's the spectrum. You see a higher energy pseudo gap. Inside the gap, you see a feature, and this feature shows below TC. Okay, so it's not the impurity state they give to you. That's the one who gave you the Bogoliubov quasiparticle. Okay, and now you can also show that, hey, indeed, at this temperature dependence, and this feature goes away at TC. Now, by seeing the Bogoliubov quasiparticle, now you can use the technique. You don't have to use the leading edge as we were struggling earlier. Now you can see the peak now in this case, and you can have a better sense of the superconducting gap. That's the transport, and you can see the peak turn on at TC, and that's, of course, we now can say is the one who's the superconducting state. So now you can see here, indeed, this is the normal state. Indeed, this feature, okay, inside actually become the superconducting feature. Okay, that's the super. It's not the piece they give you the large reconstructed Fermi surface. There were residual states that gives you the superconductivity. Okay. Again, that's again the data. So the proposal will be, say, that's the map, okay, and of the Fermi surface, and you can say that, okay, there are two pieces, okay. There's a reconstructed Fermi surface, the larger piece, a larger gap, you know, this large gap, okay. Then there is a ghost-like Fermi surface, okay. That's why we call the Gossamer, stealing the words from others. And you can see that, of course, at a higher doping, the physics goes away. Okay. So that's and that's where the superconductivity comes in. Okay. This, of course, the next thing you can see. Okay, I'm going to go around entire Fermi surface. You can see that this is the red feature, that's the anti-ferromagnetic feature, okay, coming in around the node. But consistently inside, there is a Bouguereau quasiparticle in this system. That's sort of, and the Bouguereau quasiparticle has its coherence peak showing, okay, I couldn't finish the first part. Okay, showing its maximum also at the hotspot, and I'm going to show the data. Okay, at the position of the anti-ferromagnetic hotspot, the pseudo gap is the largest, but the system was clever enough also build the strongest superconductivity. They're all at the same spot.
Theta equals 45 is the nodal point.
Yes, theta equal to zero is the antinode here, and 45 is the node. Okay, the node is in this sample is not being gapped, is being gapped by the antiferromagnetism.
It doesn't seem to go to zero at the node.
Correct.
It's a
yes,
superconducting gap.
It's a superconducting gap because you don't even have the Fermi surface. Because the Fermi surface sinks below at the node. But as you increase the doping, the node gets recovered because you have a Fermi surface. Okay, so the work Deng Hai and his collaborator did was basically taking into account the fact that the integrated moment of spin in this system is a constant as a function of doping. Okay, so saying that throughout the doping process, the amplitude of the antiferromagnetism doesn't change, but the orientation has a fluctuation. And I'm not going to go into it. With that, they can actually reproduce the result, especially this sort of the ghost-like Fermi surface. And this paper will come out soon, so those details are all in the literature. Okay. Yes.
I'm also confused about the same point Subir was. In the normal state, you think the Fermi surface looks like
just the pocket.
Just the pockets around pi zero.
There is a touch below the Fermi level, at least doping.
So, I mean, that plot there shows spectral weight there, but you don't think that's
the leaking of the spectral weight. Let me.
Because that's of a finite integration window, and that's why
you can see if you have you will see signal leaking, but you can clearly see this.
I want to look at plot G. Which one are we talking about that has this? Oh,
there's a cut one here at the node. Yes, because sometimes the map can be misled by the matrix element, and when you're in doubt, you go back to the original band. This one.
But for x equals 15 along the node, at the lowest temperatures. Along the nodal direction, lowest temperatures, there's a gap along the node, or there's no gap?
There is a gap. But there's
a gap.
This gap we can show is a particle hole asymmetric. Right. And we believe this gap is a continuation of this antiferromagnetic gap.
And the red blob there is coming in square G, there is coming because of a finite integration window.
Correct.
Okay.
Yeah. No, you can have a D-wave superconductor if the node doesn't have a Fermi surface. Yeah. What? At higher doping, you would.
Yeah, at this one.
Say it again.
At this doping?
At this doping, it can still be a nodeless D-wave because your node doesn't cross the Fermi surface.
You have magnetic long-range order, antiferromagnetic.
No, this is sufficiently high doping. Magnetic long-range order goes away somewhere around 13%, but within the plane, according to Martin, there's still.
I thought you said that the Fermi surface was just below the Fermi level. Though.
Right. Okay. Yes, correct.
There is a Fermi surface there.
There's a Fermi surface at the antinode.
No, but on the node, I thought it was at this doping. I thought you said it is a Gossamer Fermi surface.
The Gossamer, okay, I understand what where the confusion is. The big reconstructed Fermi surface does not have a node. Okay.
No problem.
Okay. There is still residual state we expect that will also have a node. However, when you're at the node, the bigger gap signal was so close that gossamer is very difficult to see. The gossamer is easier to see experimentally when the underlying band is being reconstructed, opened up a big gap. I don't know, is that clear? Yeah, what I'm trying to say is, basically try to say that to see this sort of behavior of this feature is when this red feature is pushed far away. When the red is coming very close to the Fermi level, then it's becoming harder to see this guy. That's just practical. So I'm not saying here the gossamer doesn't have a gap, okay?
I have a question.
Should I go, let me, okay, let me just, okay, Philip, you sing the song, so you have the privilege.
Okay, look, is this a question about the arc? Are you certain it doesn't go to the rho one zone edge?
For the electron doped one, you always know that the arc is sort of, because the hotspot is not in that zone, it's somewhere in between, yeah.
I just wanted to make sure of that. I'll ask another question in the...
Yes, please, okay. Okay. Again, that's but the data I hope you see is clearly, very clear. There's two features. There's one, and there's another one, and that's the lower energy one. So let me now talk about this one. This is in the regime of the long-range ordered state. That is the what you would have expected. I want to say that I'm talking about 4% or above. Okay, so that's sort of the other piece of Fermi surface now is below, and this again go back. In fact, it's already sort of hinted in Peter's thesis. I mean, I don't know whether you remembered. Looking back, those features are still gapped, but we didn't pursue that. That's again the Fermi surface like feature near antenna. That's what we are trying to do. The gap I'm talking about is very different from anti-ferromagnetic Mott gap. Okay, at half filling, the energy scale is much bigger. So already, even at 4%, there's a lot of low-lying excitations near the antinode. Okay, let me just say that this is, again, this is fairly generic. This work in Carl Shen's thesis, and you can see at a low energy there's a gap in this. But I want to say that there's also persistent reports that in those underdoped N-type systems, there is an upturn of resistivity, okay? And in this paper, the authors say there are two possibilities. One is the localization, the other some sort of condo. And they attributed, say, the condo-like thing was better. I think there was other paper trying to have some magnetic scale. So the point is that there's some resistivity. More interestingly, Rick Green's group, okay, have shown that, in fact, these systems have a gap, and that gap goes away when you turn on a magnetism. Okay. And they sort of attribute to the possibility of superconductivity in this long-range ordered state. So, and I'm going to just rush through it. You can see that's the Fermi surface for 11% doping. This is sample with a long-range magnetic order, and you see these features. The key here is that if you, okay, that's the Fermi surface pocket at antinode. If you look here, you can see these guys are very, there's a low energy excitation, and it's always being gapped. And it sort of goes away at the temperature, okay, somewhere around 40 or 50 Kelvin. And you can see that this temperature is actually quite consistent with the upturn of the resistivity, okay? And interestingly, if you look at this gap, okay, and you take the data divided by Fermi function, remember photoemission can study state above the Fermi level when they're thermally populated. Okay, you divide out and you look like this. Okay? Just to make a point, that again is the earlier data, at the antinode, if you divide things out, looks like a particle symmetric. But if you look at the nodal region, there's also a gap. If you do the same trick, you can see the data going down. It's not particle symmetric. There's another type of gap, which is none. Okay, that's why we say this was dominated, influenced by antiferromagnetism. Okay. So all this suggests that we have an energy gap at a much lower temperature scale, and that's the doping dependent, you know. By the time at the 19%, it's really gone. This gap is always there, and you can see that there's a gap and smoothly convert into the superconducting gap. And I want to say that those features are very sharp, very reminiscent to a superconducting gap. So then the question will be, we already used up antiferromagnetism. What are the other possibilities? One of them will be charge density wave. And indeed, as being reported by I think the UBC group, and showed antiferromagnetism. They see the vector here is exactly this vector somewhere here for this kind of doping. Okay, so it could be a charge density wave gap. Except this, we measure this gap as a function of doping. You see monotonically going down like this, but when you look at charge density wave, it behaves like that. Okay, both temperature dependence, doping dependent, and the temperature scale were very different. So one way to think about it is you are fighting for the same piece of Fermi surface. At a higher temperature, you probably have some sort of charge density wave as you go to down, and this one seems to be smoothly connected into the superconducting gap. And by exhausting, we have already used up antiferromagnetism, and it doesn't look like a charge density wave. What's left over, and by the fact it's so smoothly connected, it might as well be a superconductor, a superconducting gap. Okay, so again, Danghai has done this calculation and looked at various systems. I should say one more thing. This gap is a constant along that piece of Fermi surface. The doping angular independent, okay, constant gap along that piece, this piece. And he showed that contrarily, certainly early to me, and he was right, that contrarily, D wave should have a constant gap. If you have any sort of S wave, you will end up with a node. Okay. In this case, and so it's consistent. So what this results suggesting that we used to think the electron doped system had a wide range of doping and temperature seems to be a boring, long range order and all that. But what is emerging now is at least there seems to be an intruding of charge density wave. That's the, then there might be a pairing in this one. Maybe the pairing is higher than we think. Okay. As a corollary of that, immediately means that those physics need to be separated from this long-range Mach state at half billion. So certainly at 4% doping, there's a lot of low energy excitations being built up already. So this phase diagram might be richer than we think. That's what I would say the surprise is. And in discussion, if I can also talk about the riches on the whole dope part near the critical doping, because that's trying to make a connection to the non-quasiparticle aspect of it. Thank you very much.
All right, so maybe a few minutes for discussion. Questions?
Yes. Let me throw away for 30 seconds another explanation for your data in the magnetically disordered state. So first part of your talk.
First part, okay.
Another explanation is that what you see are precursors to antiferromagnetism. Not reconstruction of the Fermi surface, but transformation of spectral weight into where it should be in the magnetically ordered state. And a way to distinguish it from reconstruction of the Fermi surface is to do, if possible, MDC at different frequencies, going over the range where you get these new pieces of the Fermi surface which should not be present in the pure normal state. If it's reconstructed Fermi surface, then intensity should not depend on what frequency you do MDC. If it's precursor and transformation of spectral weight, then these pieces where you get new extra Fermi surface, its intensity should go to zero as frequency goes to zero. So this is the way to distinguish. And very quickly, second part which I want to say is that if you have precursors, and precursors come from thermal fluctuations, then of course if you look at spectral function, you have a lot of spectral weight transformed from low to high energies. But if you solve for superconductivity, thermal precursors actually cancel out on superconducting problem. And as a result, you get exactly the same superconducting problem as if precursors didn't exist. So this is what I want to say.
Thank you very much. It will be something we can look into it. I should have said also, you know, in an earlier paper by Changyang Kim's group, there's something very reminiscent. Try to say that I have a quasiparticle coupled to some sort of spin wave. Their tuning parameter would be sort of correlation length in that sort of modeling. There appear to be multiple ways to model it. I think the experimental progress I'm reporting here is to say that we see the Bogoliubov quasiparticle for the first time in temperature dependent. Then you can prove this seemingly incoherent state, okay, emerges below TC. I think that's one thing I think was a part of in this discussion. The reason we have confidence in the P-type system, all those incoherent states in the normal state, we are confident this was coming from physics rather than chemistry or disorder of material, because as soon as you cool that thing below TC, it turns into a resolution limited peak. And disorder will not do that. And the same reason, this observation allow me to say, I know those are states that really matters for superconductivity. Yes.
Yes. If you have an arc, which is a series of poles,
I have an arc, yeah.
Yeah, and it doesn't go to the Brillouin zone boundary. If you consider a path that goes through the arc and then back, avoiding the arc, there's no way to get the right sign of the real part of the green function unless you have zeros. This is just an observation. The best argument for a Luttinger surface being physically relevant to the cuprates is the Fermi arc, as has been pointed out before.
Okay.
So there are these Fermi arc deniers. You mentioned climate in the room, but there are these Fermi arc deniers because it doesn't fit into the Luttinger sum rule that they have in mind. But that's beside the point. I just want to say it's a fact. They're arcs. You can't get around it.
Okay, Philip, I would say that one of the nice things about the electron-doped system, the physics is non-monotonic. If you're in whole-doped system, this hotspot is very close to the antinode. Right. Then there are many other things happen. Then now it's so separated from antinode, then you know this maximum corresponding to the anti-ferromagnetism, and is also the region. And this can give you an insight even in the or called the pseudogap phenomenon. Right. And for this pseudogap clearly is related with magnetic order.
So if you show your main phase diagram again, at the big,
main phase.
at the beginning, yeah. So okay. Along line 1, if you go all the way down to zero temperature. Let me go to the end closer. Okay. Yeah, line 1. You go all the way down to zero temperature. Do you see the nodal quasiparticles? There, right.
Here.
Yeah, way in the superconducting state.
The answer is no.
No.
Yeah.
So at zero temperature, there's definitely no antiferromagnetism.
I would say the following.
But you think it's there, you just...
Operational, I believe it's there in the cosmos, but it's such a small percentage of the total spectral weight with a much bigger signal on top of it.
Yeah.
I cannot make a statement one way or another. That's what I'm trying to say.
What I will say is that It's possible to have D-wave superconductors without a node.
Yeah.
But it requires antiferromagnetic long-range order, or it requires some really exotic state that I don't think you're supporting.
This situation, okay, is we are not in the regime with the long-range order. 15% is beyond the long-range. But Martin has shown within the plane, actually, you still see a pretty strong correlation. So I can't give you the answer at the 0 temperature in this experimentally. Yeah,
okay.
it was a very
One more question, and then we can.
Well, we started late, I think, also. So.
Even including the start.
Okay, the chairman said that.
Yeah. So with respect to doping 0.15.
Yeah.
Did I understand you correctly that you wouldn't expect quantum oscillations there from what you see?
I would say if the quantum oscillation we'll see in similar doping region, it's a subtle thing. The reason I'm saying that we knew that even nominally 15% doping, if you anneal the sample differently, you would have somewhat different results. So it's fairly, in other words, the nominal Syrian doping is one of the parameters of that. There could be, percent of difference. That's what I want to say.
Thank you. So the reason I asked is that there is a quantum oscillation experiment on 0.15 doping.
Yeah.
So not only it shows very nice quantum oscillations, moreover, some signatures of these oscillations appear to be consistent pretty much only with antiferromagnetism.
We published this paper, compare this pocket quantitatively with the quantum oscillation. They are the same number. So we have that in this paper.
Yeah, there are quantum oscillation data by Kartsovnik and company.
I agree. And I believe we cited that result in this paper. We try to explain why you only see this piece and we don't see this piece, because the scattering rate at the antinode is much stronger. In this sample, if you look at the more subtle days, you actually begin to see this guy touch at the Fermi level. And in that case, we can show at a quantitative how much percent of the Fermi surface is for the nodal pocket. Okay.
Okay, I think we should move to the next talk. So thanks, yes, again.